Good morning, everyone. Thanks for joining us so early for this breakfast seminar. It's the 5th breakfast seminar in the series that we have for Mistra SafeChem. And today we will be presenting Mistra SafeChem's toolbox in practice, highlights from the case study. So it's a lot about the work package 6 in the program. And presenting today will be Lisa Sjölund from RISE och jag från IVL. As a program for today, we start with talking about the program and its case studies. We'll be presenting that part, and we'll give an example of one of the case studies focusing on indoor air quality. And after that, we will go on with an assessment of alternatives to silicones and cosmetics, which is the second large case study that we have in the program. Important for today, if you have any questions, just write them in the chat. You won't see them directly popping up. It might take some, and there might be a bit of a delay. But we will try and answer all the questions in the end, and those that we can't answer in time, you will get an answer to by email. In the same email after the webinar, you will also get a link to the recording so that you can view it later on as well. And we will not send out any presentations. So to start with the first presentation for today, a little bit more about what is Mistra SafeChem, a little bit about the program, and also about the case studies. So what is Mistra SafeChem? For those of you who haven't been to any of the previous seminars, Mistra SafeChem is a research program targeting green and sustainable chemistry and offering a holistic approach to chemicals. And what we mean with that is that we look at all different types in the chemical production line, but also in the use when it becomes a waste. And also we look at the production of the chemicals, we look at the safety of the chemicals, we look at how sustainable is the production. So it's really like a holistic approach there. The program started in 2020 and runs to 2024, but there is a second stage that we're currently planning as well that would then give us 4 more years in the program. The program is a consortium led by IVL, Swedish Environmental Research Institute, but has many other partners, both from research side and also industry partners. And you can see all the logos here. And if you want to find out more, you can also visit our website where all the information is, but where we also have, for example, the yearly reports where you can see what are we doing, what have we done this year, and what is planned to be upcoming for the next years. So what do we do in the program? So Mistra SafeChem is a research program. We target green chemistry and we have a holistic approach to chemicals. And how do we do that is by working on new synthesis processes for chemicals. We also have developed tools and both like develop them from start, but also further develop tools for improved risk assessment and life cycle management in a way that we can hope that we can predict and avoid risk already in the design phase. And the result of the program is then that we reach both current and future chemists. And as an addition to that, there's also a master program that's been developed within this project that focuses on implementing these green chemistry principles already in the master program. It's Mistra's largest project to date. We have 70 million in support, and the industry is contributing with another 30 million, and that's only for those 4 years then. So in short, the vision of the program is that we enable and promote the expansion of a safe, sustainable and green chemical industry in Sweden. And the way that the program is built up is that we have work package 1, in which we're both coordinating the program, but we're also doing internal and external communication. If you go into our website, for example, you will find a lot of this external communication, a lot of news updates, newsletters, yearly reports that you can find there. So I really recommend looking into our website for that. Then we have work package 2, where we try and develop a vision and agenda for green and sustainable chemistry. Here, for example, we're looking into how does the program fit into, for example, EU chemical policy? How does the Green Deal fit in here? How can we adapt the program to that? But we're also looking into what does green chemistry mean for the Swedish chemical industry? Like how do we interpret those definitions? Then we have work package 3, mostly focused on hazard and risk screening. So both to be like an early warning tool, but also to help and analyze which chemicals of concern should be prioritized for example, for substitution. Then we have work package 4, focusing on design and management of chemicals, materials and processes. Here, for example, we're looking into new enzymatic and catalytic processes that are more sustainable. We're looking into zero waste and also safety of the production. Work package 5, mostly focuses on life cycle assessment and management of chemicals, materials, and processes. It's here, for example, that we do risk assessments, LCA, LCCs. And then we have work package 6, which is the one that we will be talking most about today, in which we have the case studies. So where we actually try and take the different tools from the different work package and test them in different case scenarios, in different test cases, and evaluate how well they perform. So about our case studies, we have 3 large case studies and a few smaller case studies. For the large case studies, we have one that's focused on indoor air quality, so materials inside a car cabin that do not cause health problems. We have one that focuses on assessment of alternatives to silicones and cosmetics. And we have one focusing on green chemistry and scale up. So we're actually, there's a new chemical that's been developed and where the production process is now scaling up, and we're trying to include green chemistry principles already from the start. And then we have some smaller case studies, mostly connected to work package 4 and to new methods or new processes for producing chemicals. And those are focused, for example, on amide bond synthesis, on hydrogenation, where we're looking to using new catalysts. We have one focusing on alternative motor oil from non-fossil sources. And we have one focusing on using textile waste to produce nanocellulose. And with all these case studies, we try to cover different aspects of the program, different tools as well. So if we try and narrow that down a little bit to what we actually do in the case studies, some of the examples are, for example, that we try to find the best alternative when substituting a specific group of chemicals. This is, for example, in the siloxane case, where we have a group of chemicals and we're looking into what alternative could be a good substitute for those. Another example is for when we screen for hazardous chemicals and try to find the safe alternative for prioritized chemicals. This is, for example, what's happening in the case on indoor air cabin, where we try and see which are the chemicals that we find, which of those should be prioritized for substitution, and then which of the alternatives are the best substitute. We also have case studies where we bring a new substance to the market, try and evaluate that. Is it safe or not? If we upscale the process, if we do the upscaling, how can we do that in the best way? Can we identify early on which aspects of the production process we should improve? We also have new production processes. It's easy to say, okay, we have a new production process. We're using this new source, which is non-fossil. The whole production process is more sustainable, but it's a bit more complicated than that. So what we do here is that we also look at the whole environmental aspect of that. Is it really better? Is it really more sustainable? And if not, what are the points where we could improve that process to make it more sustainable? And then we also have for example, evaluating the use of alternative raw materials. The textile waste project is a good example there, where we use textile waste to produce something new. So why include case studies? Well, the first reason is kind of obvious. It's to reconcile the methods and processes within Mistra SafeChem. And that's because we have a very large toolbox in Mistra SafeChem that we want to look at. We want to evaluate it, but we also want to make sure that it connects in the right way. If we look at the toolbox in a bit more detail, then we have 2 big categories that we can use to split them up. On the one side, we have testing and screening tools, and on the other side, we have tools connected to lifecycle management. And then going a little bit more into detail and splitting up those tools into different categories. We have, for example, tools coupled to analytical chemistry. We have tools that are used to predict physical chemical properties. We do hazard screenings. We do environmental fate modeling, ecotoxicity testing, risk assessments, and much more, just in the first part. And then on the second part, coupled to lifecycle management, we have, for example, process modeling. We do upscaling. We do hotspot analysis. We go all the way to LCAs and lifecycle alternative assessments. So it's a very large toolbox, and I haven't even included all the details here. But what you can see is that there's sort of a trend or like a flow in this toolbox. So of course, for each of the different scenarios, each of the different case studies, you will come into this toolbox at different points. But in general, you could say that one of the first steps that could be done is, for example, analytical chemistry. You try to analyze which compounds do we find. Then you go and look more into detail in these compounds and try to look at the physical chemical properties, like What do they look like? What structure do these chemicals have? Then you can go to hazard screening, which chemicals are toxic, which chemicals form another hazards. You can do a fate modeling to see where the chemicals end up. Then you can do a toxicity testing to look more for the risks, more for the toxicity there. And then you do a risk assessment combining all that data where you actually analyze, okay, what are the risks now? We have the hazards, we have the toxicity, we have the fate of the chemical and the exposure. Now we can do a risk assessment. And that's the same with the life cycle management as well. You might start with the process modeling and then upscaling and hotspot analysis all the way to a full LCA. And what's important that we do in work package 6 then is that we try and see how does this all connect? How do we get data in the right way to go from testing and screening all the way to life cycle management and maybe back again, but also between these different tools, for example, analytical chemistry, how do we connect that best to predict physical chemical properties? Like what data is required? How do we align ourselves so that this goes in a smooth way? So a lot of the focus of work package 6 is on this. Another reason is to see how industrial challenges can be transformed into case studies. So how do we take a question that we have in the industry and make it into something that we can use in the case studies? How do we solve those problems? To evaluate the toolbox, of course, see what is working well, what is not working well, how can we improve that? And of course, also to develop Mistra SafeChem further. Maybe there's some parts or some case studies that are really challenging that we can't solve with the tools that we have right now. And then how can we develop those tools better? Not just for now in this case, but also in the next 4 years of the program, for example. And then another aspect is that we also promote Mistra SafeChem through this and also the toolbox so that other companies see or other organizations can see what are the tools that are available, how could they be used in my case, give some examples of how the tools are used as well. So it's easier to understand how everything connects to each other. So then the first case study that we will be talking about today focused on indoor air quality, and then we focus mostly on materials in the car that do not cause health problems. Then the question that pops up, of course, is why focus on the indoor air environment of cars? And that's because on one hand, cars are very complex products. They're often taken as examples of how complex the products are. There are like thousands of different components. They each have their own properties. A lot of these materials have to achieve very specific functions. For example, they have to be flame retardant. They can't age too well, age too fast because they're exposed to UV a lot. Some of the materials need to be water or stain repellent. So there's a lot of functions that go into these materials, and that requires complex chemistry as well. So that's one aspect of it. On the other end, there's also a very unique microenvironment. Cars have very good ventilation. The air doesn't really stay so long in that in the car cabin. So as a person sitting in the car, that's a good thing because the air doesn't stay too long. You get fresh air all the time. On the other hand, you have very high temperature differences. Like the summer has started now. I guess those who drive a car to work will notice as well. It gets really warm. Temperatures can get up to 80 degrees in the car. This creates a very unique environment where chemicals that might be very stuck in the materials are now released and then might deposit again when the ventilation starts and it cools down. So this creates a very unique microenvironment. And of course, the car industry has a very good system for following up on chemicals. But there's a big need to be ahead of legislation, ahead of what's going to be the next chemical that we need to phase out. And there it's an interesting case study because then we can focus on what could that next chemical be? What should we focus on next, for example? And here the goals are, of course, that we want to have materials in the car that do not cause health problems. And the focus for this case study, we narrowed it down a bit, is that we focus on polymeric additives. And as hazards that we prioritize are chemicals that are carcinogenic, mutagenic, reprotoxic, but also endocrine disrupting chemicals. So those that we find that have those properties will be prioritized for substitution. If we take back this slide that we presented in the beginning and fit in how the case study here fits in, we could say that we start in work package 3, that we are sampling the car cabin. We're doing targeted analysis. We're also discussing non-targeted analysis right now. And then we then prioritize which chemicals we want to substitute. And then for the candidate solutions, we're looking at mapping of alternatives. So when we have these chemicals that we want to substitute, they perform these type of functions in the car. What are the alternative chemicals on the market that could be used instead? Then we go on to work package 5, and we do prioritization of the risk chemicals, which is the chemical that is most prioritized for substitution, which has the highest risk, for example. Which of the alternatives ranks the best, which one is the best that we could use. And then we also look at the tools that we're using in the models, to see if we can write any guidelines for how they could be used, how they could be optimized, but also adjust them for our cases. And then, of course, there's the toolbox evaluation, looking at how did the different tools perform. Are there any knowledge gaps? What could we not respond to, or what could we not find a solution for with the tools that we had? And then also to document the decision process, because there's one aspect in doing all this from a research perspective and say, okay, this chemical is the best from the tools that we looked at. But then there's also, of course, how does it work in reality? Like, what are the other parameters that come into play into this decision process? What's important to look at? Can we learn something from that as well? What we've done here is that this is an image of the sampling of the car cabin. What you see here are passive samplers. They're underneath the aluminum foil, so it's a little bit hard to see. But what we're doing is that we're using passive sampling in a car that's inside a climate room. So a climate room that's heated up over a few days to reach those very high temperatures up to 80 degrees and then cool down again to try and simulate what could happen, for example, when the car is left in the sun for a while. And then we're looking at both air samplers and contact samplers. The air sampler's purpose of that is to know what are the chemicals that are released in the air, what do we find in the car. Contact sampler, we try and focus a little bit more into which materials do these chemicals come from, so that we can then identify where they are used. And we're doing target analysis for now, and we're discussing non-target analysis as well. Then we have 2 different tools that we're using to prioritize substances of concern. So on the one hand, we have USTOX, which is a consensus model endorsed by UNEP and focusing on the LCA aspect as well. And then we have ProScale, also a life cycle oriented method to assess toxicological potential of product systems. In a very broad way, we could categorize USTOX as focusing more on the use phase of the product and the waste when it becomes a waste, and ProScale more on the production of the chemical and the production of the materials. And we're using both of these models in the case studies, or both of these toolboxes in the case studies. And what we're doing is that we're seeing in which cases does USTOX is USTOX more relevant in the case study, and which one is ProScale most relevant. And also for USTOX, for example, we're looking into how can we use it best in our case. For example, the indoor car environment is not an environment that's originally built into USTOX as a model that can be used. So there we're looking into how can we develop that car environment model, and also how can we make it easy to use. Because in a lot of the cases, suppliers, for example, to the car industry, are not willing to share their data directly, but they could be using USTOX themselves and then share the output from that into, well, to the car manufacturer. So we're also looking into that workflow. How does it work? How can we adapt the program to make it more easier for that? And then, of course, we have to find, of all the alternatives that we have to find the best. And here we're using a tiered approach from developed by Peter Fonke and his colleagues from DTU. And there we have, for example, we have the pre-screening, which is the chemical analysis that we've done before to identify which chemicals we want to focus on. And then there's a stepped approach where we screen in more and more detail over time. So we start, for example, in tier 1, where we screen a large set of alternatives at a more basic level. And then at tier 2, we also include a chemical supply chain. And then tier 3, we also look at the product life cycle, because it takes so much time to collect all this data and to perform this analysis. We try to minimize that and focus on, for example, tier 1, where we already can exclude a lot of the chemical alternatives. And then maybe for the best alternatives, we go to 2 and 3. The next step in this case study is that we will do a second sampling campaign where we will focus on some new materials that can be used in the car cabin. We will also be adapting USTOX for use in the indoor air environment of cars. We will start prioritizing chemicals of concern based on the results of the sampling campaign. And then we will start this tiered approach to screen for the best alternatives. And this work is done. We have a small core team consisting of my colleagues Maria Benander from Volvo, Marie Gottfridsson from IVL, myself, and then we of course have a lot of support from the other experts in the group of SafeChem. So for example, on the LCA side, we have Hanna Holmqvist, we have in silico screening by Swapnil and Ulf, we have on new stocks, we have Peter Funk and Olivier as a support. ProScale, we have Thomas Rydberg, and on sampling and analytical chemistry, we have Joris Gunnar and Jon. And with that, I'd like to hand over to my colleague Lisa.
So, hello. I will talk about the case study where we search for and assess alternatives to silicones in cosmetics. Silicones are widely used in cosmetics, and we have done a mapping of silicone uses and found that there are many different types of silicones used, and we can divide them in low molecular weight and high molecular weight silicones. And the different silicones have different functions in a product. But if you look at the low molecular weight ones, we have the cyclic siloxanes, linear ones, branched, and then we have the high molecular weight ones, which is more the polymers. So it's a large group of chemicals. So why are we looking for alternatives? So there are chemical restrictions of the cyclic siloxanes. So for example, D4 is prohibited in cosmetics. D5 is restricted in wash-off cosmetic products, and we also have a wider proposal for a wider restriction of D4, D5, and D6 in different types of products, including cosmetic leave-on products. And we also have D4, D5, and D6. They are listed as substances of very high concern. So there are chemical restrictions that that is sort of one of the driving forces for searching for alternatives. But there is also an emerging incentive for finding sustainable source material and green processes. And it's in cosmetics, it's a big trend with bio-based and natural ingredients. And the degradation and environmental fate is very important, especially when it comes to cosmetics. So there are different reasons for making this alternatives assessment. And before we started to look for alternatives, we wanted to better understand what are the concerns for the silicones. We know they are restricted, but we wanted to better understand what are the concerns to know how to benchmark the alternatives. So we did a life cycle mapping. So as we have looked at both the production, the use phase, and the end of life to see what potential concern do we foresee in the different life cycle stages. So there's a lot of information collected or summarized in this figure, but I will try to summarize. So if we start looking at the production, there are some concerns in that the process of making silicones is it's a very energy demanding process, and cyclic siloxanes are used together with a potential ozone depleting substance to make the silicones. And then when we look at the use phase, there are some toxicity concerns of especially the cyclic siloxanes. That's why they are also restricted. And I would say that there is also quite a lot of data gaps for many of the silicones in terms of toxicity. And the cyclic siloxanes are restricted due to that they have the PPD concerns, so they are considered to be persistent, bioaccumulating, and toxic. So the end of life is an important aspect of the silicones. And we know that the wastewater treatment plant doesn't really capture all of the silicones. So we do have emissions of silicones from wastewater treatment plants into the water. We know that the silicones are especially persistent in sediment and soil. And we also know that there's a quite complex degradation process of silicones, and that also cyclic siloxanes can be formed both during insertion but also in the environment. So with this altogether, it motivates for the search for alternatives to silicones. So we, as I said in the beginning, there are a wide range of silicones that are used. We had decided to focus on D5, the cyclic siloxanes, which is restricted in wash-off products. And we have also decided to search for alternatives for dimethicone, which is the most widely used silicone in cosmetics. In order to do some kind of benchmarking in the end, we have decided to focus on the use of these silicones in a liquid foundation. So D5 is used at 20% in a liquid foundation, and dimethicone is also often used in liquid foundation. So this is sort of our benchmark product that we will consider when we do a product life cycle in the end. So the approach to search for alternatives, we have used different strategies to find alternatives. We have focused on chemicals that are approved to be used in cosmetics, so available alternatives on the market. We have searched different cosmetic ingredient web pages. We have had contact with suppliers, and we have also looked at commercially available products on the market that do not contain silicones, and try to see what do they contain instead. And when it comes to foundations, there are some available alternatives. There are not so many, but the driving force there has been to the natural-based, the bio-based ingredients. That has been the driving force for not including silicones there. So when it comes to finding the alternatives, it's not really about finding the perfect alternative. Of course it's good if we find a perfect alternative or alternatives, but it's more about establish the process, how to evaluate alternatives, and then considering the whole life cycle. So this illustration was also showed by Damien. It's from Peter Funke and colleagues, and it illustrates the life cycle-based alternatives assessment, is the tiered approach. And we have already decided to look for alternatives to silicone. That's the sort of pre-screening. So we are now more in tier 1, where we screen a large set of alternatives, and we compare the different chemicals for consumer risk and ecosystem impacts. And then the idea is that we identify the most promising ones and continue with those in tier 2 and tier 3. So using the different strategies, we did find 172 different alternatives, and that's quite many. So we need to prioritize and see sort of which ones seem most promising from a hazard and perspective. So we have used the Safe by Design framework. It should be noted that this is really a draft, and it's being developed at the moment, but we have used this as a tool to prioritize among our alternatives. And before, like the first cutoff that has been used is that no substances that doesn't have any CAS number, they are not passing cutoff, because we need information about the substances in order to evaluate them. So that leaves us with 158 alternatives to evaluate. And then this is also from the Safe and Sustainable by Design criteria or the framework. So we have followed this framework, and we have given our alternatives a score, like a safety level score. We have a cutoff criteria that the alternatives has to pass in order to even be considered further. But then we also have, and that's removing the most harmful substances. And then we have safety level 1, it's substances of concern. And then we have other safety levels. So the tools to search for and classify the alternatives in terms of these levels, we have used different tools such as ChemHat, Pharos, ECHA, the ChemSec list, and PRIO, etc. And to summarize, this is an overview of our prioritization. So 14 are removed because they don't have a CAS number, and it should also be noted that 60 alternatives are removed because they are not registered in REACH, and out of the ones that are registered in REACH, 5 are removed because they don't have any dossier content in terms of PBT assessment, skin sensitization, and mutagenicity. But then we can see sort of how many alternatives are removed for the, in the different safety levels. And that leaves us with 23 prioritized alternatives that sort of passes and fulfill all the criteria so far. I want to highlight also the Mistra SafeChem in silico toolbox. So we have screened the alternatives with the Mistra toolbox in silico toolbox from VP3. And here we don't have the chemical structures of all the alternatives, but the ones that we do have chemical structures of, those have been screened. So we used the SMILES notation to do the assessment. And the tools that have been developed or further developed in the Mistra SafeChem are endocrine endpoints, bioaccumulation, reproduction toxicity, liver toxicity, mutagenicity, and persistence in soil. So out of the alternatives with structures, 45 were removed, were showing a positive impact for at least one impact category. And out of the ones that had not been removed, sort of, or that didn't have any hazard data, showed positive for at least one impact category. So this has been yet another tool to make the prioritization. This doesn't mean that these substances will not be further considered as a possible alternative, but these have been given the safety level score of 2 that needs more look into. Another tool that we have been using for then the most promising alternatives are skin sensitization and eye irritation, and these are also tools that have been developed in the program. Here it builds on the Hansen solubility parameters and the Hansen 3D space. So basically, a substance can be described by its dispersion, hydrogen bonding, and polar properties. And there has been developed a sort of we know where the skin is and where the eye is sort of located more or less in this Hansen space, and it builds on solubility and equal solves equal. So if we have the alternative, we can predict the Hansen parameters from the SMILES, from the structure. And if the substance falls outside the green sphere for the skin, it's predicted to be non-skin sensitizing. And when it comes to eye irritation, a substance that falls inside the green sphere is then considered eye irritation. So this is, so if we summarize the more promising alternatives based on skin sensitization, eye irritation, and also prediction of biodegradability, it gives us an indication that maybe one of these should be considered to maybe not be less safe alternative. Another important aspect is sort of the transformation of the components in the environment, and here we also have a tool to predict what metabolites are formed in the environment, and then we can make a similar hazard screening and in silico model of the metabolites to make sure that an alternative that is considered safe as is doesn't break down to any hazardous metabolites in the environment. This is also a tool that we have tested and will be testing further for the alternatives. So far, I talked more about the inherent hazard properties of the chemicals, and basically that we have used this safe and sustainable by design criteria as a tool for us to prioritize our alternatives. It doesn't mean that it's the final list, but it's more our prioritization, and then we see it as an iterative process, and we look into sort of including also alternatives with the safety level 2, for example. But then, of course, it's about not only the hazard properties, but also about the exposure. So in the risk assessment, the exposure is also considered. And if we look at the SSBD framework, and if we move to step 2 and step 3, the exposure is considered. So we have 2 tools that Damien talked about. We have ProScale that is considering more the exposure and the risk when it comes to production. And we have UseTox considering more the health and environmental impacts from the use phase. So if we look at UseTox, it's a consensus model for human toxicity and ecotoxicity characterization, and it considers both the near field and the far field exposure. And we are using UseTox. We can use it as the tools for risk assessment and further prioritization of our alternatives. And the idea with UseTox is also to estimate characterization factors that will be used for the LCA assessments of the product in the end. And this has been developed by Peter Franke and colleagues. So we have tried UseTox and implemented in our case study. We have only so far looked at the near field exposure. And once you have the alternatives, the prioritized alternatives, we have looked at various types of input data. So it's both physical chemical properties of the alternatives. We need some toxicity data, such as the reference dose and the effective dose, and water solubility and different partitioning coefficients. And considering the exposure, we also think about sort of the concentration of the substance in a product, how much are you exposed to on a daily basis, and for how long time do you have the product on your skin. So finding data for some of the alternatives, we can then use UseTox and predict this hazard quote which is supposed to be less than 1. And here, this is just the first screening, but it's interesting to see also that for many of the alternatives, there's a higher exposure for inhalation exposure than dermal exposure, even though you apply the products on the skin. So further use of USTOX will then be used to quantify these characterization factors, both for human and ecotoxicity, and then we will implement that in a full product life cycle assessment, where we will compare the most promising alternatives in a product and benchmark that against a product containing silicones to make sure that we are capturing all environmental impacts, including the chemical risks in the life cycle. And this shows not that this is an example from another study, but they are involved in the project and they are developing ProScale and USTOX. So this is more to visualize that we want to, in the end, compare a liquid foundation, in our case, including both the chemical footprint of the ingredients, but also considering and compare it with sort of the climate change, for example, and other environmental impacts that are normally quantified in a life cycle assessment. So if we look at the next steps, we want to do further evaluation of alternatives with the Mistra toolbox, and this includes in silico hazard models, biotransformation modeling, to see what could potentially be formed in the environment, hazard evaluation, and USTOX and ProScale. So continue the evaluation with the toolbox, and the aim is to find the most promising alternatives and quantify the characterization factors and make a product assay and benchmark the alternatives with a product containing silicones. To really make sure that doing a substitution to one of these alternatives really provides a better life cycle for the product. We see this as an iterative process. We have done a first prioritization, but we see a possibility, of course, to further evaluate and pick and remove and add substances with other safety levels, not the ones that didn't pass the cutoff, but to look for other alternatives as well. And in the end, we also want to do some formulation work to practically compare both the function and the skin feel of silicones and the potential alternatives. And the skin feel is important because one of the main reasons, one of the main functions of silicones is that they provide a quite nice, smooth, nice touching feel and a nice perception on the skin. So with that, I want to highlight all these competent colleagues, both from RISE, H&M, and IVL, that have contributed to this case study.
And with that, we continue to the Q&A session. We now have 2 laptops here, so we'll try to do it in the best way possible. And we actually already had some good questions that came in the chat, and we will try to go through them. If you have more questions, just write them in the chat. Preferably also write your name and organization so we know how to refer to you, and that you can easily find your questions back when you get the webinar in the email, or the link to the webinar in the email, and then the question that we haven't been able to answer right now in this session. The first question was from, I think, from Matthew McLeod from ACES. regarding the Peter Funkin's tiered approach to assessing the best alternatives. And there the question was regarding tier 0, where you then first screen for chemicals that are fit for purpose and fulfill the desired function, and to see if there ever is a decision point as well where we can focus more on, for example, reconsidering the product design and leaving out the function in order to get a safe and sustainable solution. I have to say here, it's been a while since I read Peter's paper, so I can't really say with certainty if that's discussed there or not. I think it was discussed there, but I can say that in the discussion that we've had, this question has popped up quite a few times. We also have ChemSec, for example, it's trying to drive as well. ChemSec is part of the project, trying to drive in the project as well that safe and sustainable should be above everything else. But here in the case studies, with how far we've come yet, we haven't really gotten to that point yet. I think once we do the tiered approach and once we see that certain chemicals or certain functions maybe are better just left outside to approach the safe and sustainable level, then that is something that we can discuss and also document that in how did that decision process go. So that's definitely part of the discussions that we're having.
No, if it comes to the silicones, if it would have only be the cyclic siloxanes, I mean, they are used in the production of making silicones, but I also know that there are ways, it's not very common, but there are ways to produce silicones without using the cyclic siloxanes. So that could be a way to remove the cyclic siloxanes. I'm not sure then if the cyclic siloxanes still can be formed in the environment, because it seems to be quite a stable sort of breakdown product. But yeah, for the silicones, that could be one thought related to that, I think.
Yeah, and actually, Matthew commented more on that as well. I will publish it in the chat so everyone can see it. It's also that who then gets to do, or who then should do the risk analysis. I lost your question here, Matt, so I'm trying to find it again. Here. So if we aim to achieve circular economy, we need to achieve a high degree of standardization of materials in, for example, cars, so that recycling is feasible. And then the question is, who should be doing this safe and sustainable analysis? Maybe it should be done only at a continent scale by EU agency like ECHA, and then a list of 2 or 3 acceptable alternatives given to all European industry. I think that's a question that we will take with us, and that will also be discussed more in work package 2 and more in the big perspective. How can SafeChem here and the platform that we're trying to develop play a role here for these kind of questions? Another question was regarding the use of in silico tools and polymeric materials. So how to use in silico tools and polymeric materials? Obviously D5 is a distinct structure, but most of the silicons you showed were polymers, so calculations may be more difficult. I think I can leave that question to you, Lisa.
Yeah, I mean, we have run use talks on D5 as a sort of starting to test, and the dimeticon was not possible to evaluate with use talks. It's out of the applicability domain.
Yeah,
it says a very it's very hydrophobic, and it's not water soluble, and it has a very high KOW partitioning coefficient. So it's so not, and I guess it's for different types of tool. We saw that some of the alternatives were not possible to predict in terms of Hansen solubility parameters, and so there it will be challenges, I would say, and we cannot use all the tools on all the chemicals, that's for sure.
Yeah, and I think when it comes to polymeric materials as well, is that we are currently focusing mostly on the monomers that are often the more toxic part, and that it becomes a sort of worst case scenario there that we're focusing on.
But I guess that's also part of VP6 to really understand, okay, what tools can be used for what substances and when in the process, and so that's a little bit one one part of EP6 is to make this sort of map what can be analyzed and what cannot, and what should be used for a specific question, for example.
Yeah, an important part there is as well that we're also looking at degradation of the compound. So what happens after the project has been used, or the chemical, once it degrades, what substance does it form, how long is their half-life, how toxic are they? So there's also a focus on that in work package 3, for example, that they're really looking more into detail into degradation, both degradation rates, but also predicting degradation compounds.
And I would also maybe add to that we, for quite many of the chemicals that we sort of see, there are also quite a lot of data gaps. So there is quite a lot that we don't know about many of the chemicals. Yeah,
which is also something that we're focusing on. How can we plug those data gaps? How can we, for example, substitute them or supplement them with in silico data? And how can we do that in the best way? And then if we find data, how do we prioritize between different data sources or different data qualities? There's another question for you here, Lisa. It's from Christer. What fraction of cosmetics with silicones in Sweden are produced in Sweden?
What fraction of
cosmetics with silicones in Sweden are produced in Sweden?
I would say that I don't think the production in Sweden is very large. I think many companies, there are several Swedish companies, but the production is outside Sweden, in Europe and Asia. If that was an answer to the question, I'm not sure.
I think so. Otherwise, you can write in the chat, Christer, and we will follow up on that.
But in terms of cosmetics, there are quite many. It's many products that do contain silicones. If that's maybe could potentially also answer that question.
Yeah. And then we've actually run out of questions. So if there are some more questions, we have a few more minutes. You could ask them now. Otherwise, we will proceed with the next part. Questions that come later as well, we will try and answer them in the email that is sent out, so you don't have to worry.
I think, also what's traditionally, I think it's, for cosmetics, it's really the use phase. It's of course of priority because you apply products on your skin and you are really exposed to the chemicals. But it's more and more awareness about you should also consider the production, and it's also important to consider the end of life, but that's more emergent, and that has not been the case always.
There's a new question that came up. Let's see. Are you able to perform them both biodegradability and ecotoxicity analysis? That's a yes. In work package 3, we offer both those tools in both of them. And what we're looking at is how do we use those tools in the best way to then give the data that is needed to make this sort of analysis. So, but yes, we have tools for both. And with that, I would like to continue to our closing slides. So, like we said in the beginning as well, this was the 5th breakfast seminar that we've had. If you missed any of the previous ones, they're all available online. So just visit our website, mistrasafechem.se. You might have to register for the seminar in order to get access, but all of them are available for free, so you can watch them. And they focus on, for example, the different work packages that we have. So the first one is more work package 2, then there's work package 3, 4, 5, and today was work package 6. So if you want to know more about the tools, for example, focus on the ones on work package 3 and 5. If you want to focus more on new catalytic methods, new sustainable chemistry, new processes, focus on the one from work package 4.
That's highly recommended. We have only sort of briefly more showed how they can be implemented, but to really know more details, I would really recommend to look at this earlier breakfast seminars.
No, but exactly. I would also like to invite you to the Mistra SafeChem program symposium, where we will have keynote speaker Paul Anastas, sort of the father of green chemistry, and that will be on the 26th of September in Göteborg. And for more information on that, we also refer to the website where you can register. With that, we'd very much like to thank you for listening. Thank all our partners as well for being involved in the project, and we will hope you have a very nice day. Thanks.
Yes, thank you.